All right, let's dive into a paper that's making waves. Robot data curation with mutual information estimators.
Yeah, this one's exciting, tackling a problem that's been kind of lurking in the shadows in robotics.
Data quality, right?
Exactly.
Because unlike those massive image data sets with millions of labeled examples,
We're often stuck with data that's limited, messy, noisy, you name it, in robotics.
yeah, totally.
Imagine trying to teach a robot to, I don't know, make a perfect souffle.
Okay.
But your training data comes from a bunch of people who've never even boiled water.
Huh. That's a recipe for disaster.
Right. You need a way to separate those culinary masters from the kitchen catastrophes.
And that's where this paper comes in?
Exactly. And the authors really hit us with a wake-up call right off the bat.
Oh, yeah.
They point to the Troy dataset. It's massive, right? But get this. Using it actually hurt performance when they tried to train a policy.
Wow, that's a pretty clear sign that more data isn't always better.
Exactly. It's a stark reminder that we can't just blindly throw data at a robot and expect magic to happen.
So what's the solution? How do we sift through the noise and find those golden nuggets of demonstrations?
Well, the authors argue that the secret sauce lies in mutual information.
Mutual information. Okay, break that down for me. It sounds a bit technical.
It is, but it's actually pretty intuitive once you wrap your head around it. It's basically a measure of how much knowing one thing tells you about another thing.
Okay.
So in this case, we're looking at how much knowing the robot's current state tells us about the action it should take.
Got it. So like if we know the robot's arm is reaching for a cup, we have a pretty good idea that the next action might be to grasp the cup.
Exactly. High mutual information means the robot's actions are predictable based on its state. You can think of it like a well-choreographed dance. Every move flows naturally from the one before it.
Okay, I'm starting to see the connection. So a good demonstration, one that leads to effective learning, should have high mutual information.
You got it. And the paper takes this idea a step further by breaking down mutual information into two key components. First, minimizing action entropy.
Entropy? Okay, another technical term. Help me out here.
Think of entropy as a measure of randomness or unpredictability.
Okay.
So minimizing action entropy basically means we want to reduce the randomness in the robot's actions.
Makes sense. Less randomness means the robot's behavior is more consistent, which should make it easier to learn from.
Exactly. Now, the second component is maximizing state entropy.
Okay, so we're trying to maximize entropy here. How does that fit in?
Well, with state entropy, we want the robot to see a wide range of states during training. This helps the robot generalize to new situations it hasn't encountered before.
Ah, I see. It's like giving the robot a more diverse training curriculum, exposing it to all sorts of different scenarios.
Precisely. Now, putting all of this into practice is where things get really interesting. The authors introduced their method, DemInf, which stands for Demonstration Information Estimation.
DemInf, I like it. It's catchy.
Yeah, and it's a clever three-step process. First, they tackle the challenge of dealing with high-dimensional data, which is super common in robotics. We're talking about images, sensor readings, all that stuff.
Right, that can be a lot to process.
For sure. So they use a technique called Variational autoencoders, or VAEs, to compress all that high-dimensional data into more compact representations.
Okay, so we've condensed the data into manageable chunks. What's next?
The next step is where they estimate the mutual information. They use a k-nearest neighbors technique, which is particularly useful for smaller data sets, something we often deal with in robotics.
Right, it's not always easy to collect tons of robot data.
Exactly. So this k-nearest neighbors approach is a more efficient way to get those mutual information estimates.
Got it. So we've got our compact data representations, we've estimated the mutual information. What's the final step?
The final step is where they use those estimates to give each demonstration a quality score. They're essentially ranking them based on their contribution to the overall mutual information.
So with DemInf, we're not just hoping for the best, we're actually selecting the data that's most likely to lead to a well-trained, high-performing robot. That's pretty cool.
Absolutely. It's all about shifting the focus from quantity to quality.
And recognizing that not all data is created equal. That's a crucial insight, especially in robotics where data collection can be so time-consuming and expensive.
Couldn't agree more. Now, before we get into the nitty-gritty of how DemInf actually performs, let's zoom out for a second and talk about the broader implications of this work. What could this mean for the future of robot learning?
Yeah, that's a big question. What does a world where we can effectively curate robot data look like?
Well, if DemInf lives up to its promise, we could be looking at a future where robots learn faster, generalize better, and ultimately become more capable and adaptable in real-world environments. And that's a pretty exciting prospect, wouldn't you say?
It definitely is. But how do we know DemInf actually delivers on these lofty promises? We need to look at the experiments, right?
You got it. Let's see how DemInf stacks up when put to the test in both simulated and real-world robotic tasks.
All right, let's dive into those experiments and see what DemInf can really do.
Sounds good to me. Let's do it.
So let's get into it. Does DemInf actually work?
Well, the authors didn't just stop at the theory, they really put it through its paces. They ran a bunch of experiments both in simulation and on real robots.
Okay, so they really wanted to see if it could handle the real world.
Exactly, and the results are pretty impressive.
Lay it on me. What kind of robot tasks were they using to test DemInf?
They started with RoboMimic, a simulated environment where you can test all sorts of things. One of the tasks involved a robot arm moving a can between bins.
Okay, classic robot stuff.
Right, so they trained a policy using data filtered by DemInf and compared it to policies trained on all the data or just a random subset.
All right, what happened? Did DemInf make a difference?
Big time. The policy trained with DemInf's curated data just crushed the others.
Wow, so it really does seem to be picking out the best demonstrations.
Yeah, it achieved over 10% better performance.
Okay, that's a pretty significant improvement.
It really shows that using the right data makes a real difference.
All right, so it works in simulation. Well, what about the real world? You know, with all the messy unpredictability that comes with it.
That's a great point. And they didn't shy away from real-world testing either. They tested DemInf on a Franca robot.
The Frankie Emeka Panda, right. I've seen those. They're pretty cool robots.
Yep, that's the one. It's a really popular research platform. They had it doing tasks like putting a pen in a cup and stacking dishes.
Those seem simple enough for a human.
They do, right. But for a robot to master those reliably, it's actually pretty challenging.
Oh, I'm sure it is.
And the really fascinating part is that even with a smaller data set, as long as it was filtered by DemInf,
Okay.
it still outperformed using all the data or a random subset on these real-world tasks.
Wow, so even with less data, as long as it's the right data,
Exactly.
DemInf really seems to be a master curator.
Yeah, it highlights how important being selective with your data is in robotics.
We were talking earlier about some of the limitations of DemInf, like how it focuses on individual actions rather than the whole sequence,
Oh, yeah, that's right.
like judging a dance based on single steps instead of how it all flows together.
Exactly. Did the authors look into that at all?
Yeah, they did. They specifically investigated the impact of the key nearest neighbor parameter. You know, that plays a big role in how they estimate mutual information.
Oh, right.
And they found that DemInf's performance was pretty robust to different values of k, so it doesn't need to be super precisely tuned.
Oh, that's good. So it's not too sensitive to that parameter.
Right, it seems pretty stable and forgiving. Did they find anything else interesting while they were exploring this?
They did notice that the choice of the nearest neighbor estimator actually mattered.
Interesting. What do you mean by that?
Well, they looked at different estimators like KSG, by KSG, and KL.
Okay.
And the KSG estimator consistently performed better than the others.
So it's like choosing the right tool for the job.
Yeah, exactly. The estimator is a really critical piece of the puzzle. It shows that while DemInf is a really powerful approach, there are still nuances to explore and refine.
That makes sense, but overall it sounds like DemInf is delivering some pretty compelling results. What do the authors highlight as the next big steps for this research?
One area they're really excited about is extending DemInfs to multitask settings.
Oh, right, because most robots in the real world need to be able to do a lot of different things, not just be a one-trick pony.
Exactly. Think about a robot chef that can chop veggies, stir sauces, and flip pancakes, all like a pro.
Now that's a robot I'd like to have around.
Right. Being able to identify high-quality demonstrations across those multiple tasks, that could really accelerate robot learning.
It would make them so much more versatile and useful in real-world settings.
Absolutely. Another promising direction they mentioned is scaling up DemInf to handle those really massive data sets we talked about earlier, the ones with millions or even billions of demonstrations.
Oh, wow. That sounds computationally intense.
Yeah, it would definitely require some serious computational firepower. But if we can figure that out, just imagine the possibilities.
We could be training robots on a scale we've never seen before and finding those truly exceptional demonstrations.
It would be like having a super-powered magnifying glass, zeroing in on the most valuable data amidst all the noise.
That's an amazing thought. It could revolutionize the field.
It could, for sure. But before we get too carried away dreaming about the future,
Right.
let's bring it back down to earth for a moment and crystallize what we've learned about Demim and what it means for the world of robotics.
Okay, yeah, let's recap the key takeaways from this paper.
Sounds good. So first and foremost, this paper really challenges that idea that more data is always better.
Right, it's all about quality over quantity.
It really highlights how important data quality is for robot learning.
Yeah, it's not enough to just have tons of data.
You got to be picky about what you feed your robots.
Exactly.
And DemInf gives us this powerful new tool to sort through all the noise and find those really good demonstrations.
Using mutual information to zero in on the demonstrations, where the robot's actions are clearly connected to its state,
Right, making sure those actions make sense based on what the robot is sensing and where it is in the task.
leading to much more effective learning.
And they didn't just talk about it, they actually tested it rigorously, both in simulations and on real robots.
Yeah, we saw how it crushed those other methods on the can sorting task and those Franca robot tasks.
Even with less data, as long as it was the good stuff, DemInf came out on top.
That's huge for robotics. It means we can potentially train robots faster.
Using less data and less time and still getting better results.
Robots that can learn new skills more efficiently, adapt to new situations.
Yeah, that's the dream. Robots that can handle all the complexities of the real world.
Now, of course, no method is perfect. We talked about some of the limitations of DemInf.
Right, like how it's currently focused on individual actions and might miss the bigger picture of the whole sequence.
Like judging a dance based on a few isolated steps instead of the entire choreography.
Exactly. But the authors do acknowledge these limitations, and they have some interesting ideas for future research.
Like extending it to multitask learning.
Yeah, so robots can learn a whole bunch of skills.
And scaling it up to handle those mega data sets with millions or even billions of demonstrations.
That would be a game changer, being able to find those golden nuggets of information in these vast oceans of data.
This paper really is a call to action for the robotics community.
To make data quality a top priority in robot learning.
Not just collecting more data, but curating it, refining.
Making sure it's the good stuff.
So for all the AI researchers and ML engineers out there listening,
Here's a thought to chew on.
we've seen how DemInf works for imitation learning.
But what about other types of robot learning? Could we use mutual information to assess data quality for reinforcement learning?
Or unsupervised learning.
If we can make sure we're using high-quality data across all these different learning paradigms.
The possibilities are endless.
It's an exciting time to be working in robotics, that's for sure.
Thanks for joining us on this deep dive into the world of robot data curation. If you found this discussion insightful, we encourage you to check out the full paper. There's a wealth of detail waiting to be uncovered.
And remember, it's not just about the quantity of data, it's the quality that truly counts when it comes to building intelligent robots.
Until next time, keep exploring, keep learning, and keep pushing the boundaries of AI and robotics.